So I'm going to record this on the computer. Okay, and now that I've started the recording, can you please put your name into the chat? Because now, if you wrote your name before I started the recording, then it's not going to be there when I look at the recording. So even if you wrote your name already, can you type your name into the chat one more time, please? And that way we'll have an attendance for everybody, and hopefully Sange will be here a little bit later today, and so she can take her attendance also, and then we'll have a full list for everybody. Okay, so yeah, so everybody can type their name in at now or at some point later. Okay, so welcome everybody. I hope everybody had a good week. And so what we're going to be doing is finishing up our unit on bearings today, bearings and vectors, and then we're going to start our unit on matrices. Okay, again, please keep yourself on mute if you're not talking, because the background noise is very distracting to the rest of the class. So yeah, so we're going to finish our unit on bearings with a more complicated bearing problem, and then we're going to start a unit on matrices, which, if you were in the course last semester, then you saw a little bit of what we're doing today, but we will quickly get into things that we didn't see last semester, probably not today. Today will be review, but next week we'll get into topics that we didn't do in the spring. Okay, so but first I want to just go over the homework like we usually do. So let's just first recall that with bearing problems, just recall what a bearing is. Sorry, it's taking a bit of a long time for this to scroll. Okay, here we are. So remember that a bearing is an angle that we measure clockwise from the north, right? We go this way, we measure it clockwise from the north. And this is not always the standard mathematical convention, but we do generally use bearings when we're talking about movement on Earth. So ship navigation or flying or running, something like this, then bearings are often used. And remember that we had this diagram last time that if I have 2 points B and A, if this is B and this is A, maybe let me draw this a little better. So if this is B and this is A, again, please keep yourself on mute. Please don't unmute yourself. So if this is B and this is A, we draw, a line pointing northward from A and a line pointing northward from B. And then we say that the bearing of B from A, we draw this line from A to B, and we have this northward line, and this angle here is 35 degrees. And so that would tell us that the bearing of A from B is 35 degrees. Sorry, everything is going a little bit slow with the internet. Let me just try to close a couple of other apps. Maybe that'll make my internet a little faster. Let me just close a bunch of things. Hopefully this should help. Okay, so all right, and let me actually close a couple of web pages also. Okay, this should help. All right, so we say that B has a bearing of 35 degrees from A. And then likewise, if we want to know what the bearing is to get to A from B, you have to start on the northern direction from B. So you start on this line coming out of B. I am using the screen, by the way, Clinton. Can people see the screen? Can people see the screen?
Yes, the screen is clear.
Yes, okay, yeah, screen is clear. Okay, so okay. Hopefully it might just take a little time to update. Okay, so this bearing northward from B, you have to go all the way around in the circle to get to A. So that's what this is going to be. It goes all the way around until you get to A. And it turns out that this angle here is going to be 215 degrees. Okay, that angle is going to be 215 degrees. And we saw last time that if you know bearing of B from A, then to get the bearing of A from B, you subtract or add 180 degrees. Okay, so to get the bearing of B from A, to get the bearing of A from B, you either subtract or add 180 degrees. Okay, and if your angle is less than 180 degrees, then you have to add. And if your angle is more than 180 degrees, then you have to subtract. Okay, so if the bearing of B from A is 35 degrees, then the bearing of A from B, we're going to have to add 180 degrees. And so it's going to be 215 degrees. Okay, so this is what we recalled with bearings. And in general, when you're given bearing problems, you really just want to draw a picture. And usually if you can draw a good picture, then you'll get all of the information you need to know from combining the picture with a little bit of trigonometry using right triangles. Okay, so this is, recalling what's going on with bearings. So now let's go back and look at the homework problems. There are only two problems, and neither of them is that bad. There will be a homework problem tonight, which is a little more difficult. Okay, so the homework problem 1. So this was originally asked to me in a WhatsApp chat. So Salifu walks 500 meters due north, then 250 meters east, and finally 500 meters at a bearing of 055. Remember what 055 means. This just means 55 degrees, right? So then, if Salifu started walking at the origin, what point is he at now? Right, so what we really want to do is just draw a picture, right? So he's starting at the origin. So he starts by walking 500 meters due north. So this is 500 meters due north. And then 250 meters due east. So east is to the right. This is 250 meters. And then 500 meters at a bearing of 055. Okay, and so what does this mean at a bearing of 055? Remember, we're just going to draw this northern line. And a bearing of 055 means that we have an angle 55 degrees clockwise from this upward pointing line. So a bearing of 055 is going to be something like this, where this angle is 55 degrees. And so Salifu's at this point right now, right? So this point is going to be called X, Y, right? So the point is X, Y, and we need to figure out what is X and what is Y. And we started at the origin, right? So the point that we start at is 0, 0. Okay, so I think maybe just because my internet is not so fantastic right now, so going back and forth is maybe going to be difficult. So I'll say a little bit more about how I would do this, right? What I would do is I would just go point by point and figure out what each point is. So if we start at 0, 0 and we walk 500 meters due north, then this point is going to be, well, still 0 in the X direction, but it's going to be 500 in the Y direction. And now if we start at 0, 500 and we move 250 meters east, then the 500 will stay the same. That's the Y coordinate, but the X coordinate will increase by 250. So this point here will be 250, 500. Right? Everything is being measured in meters. And so now the last part's the more involved part. So we have 250, 500, and now we're going to go 500 meters at a bearing of 55 degrees. Right? So what we're going to need to do is build a little right triangle, right? Every time we need to do this, we try to build the relevant right triangle. And so usually if you have a line that you're walking along or driving or flying or navigating a boat, then that line will be the hypotenuse of the right triangle. And one of the other sides will be the north-south line, and the other leg will be the east-west line. Okay? So we have this triangle with an angle of 55 degrees over here, and with one side equals 500 meters. So what can we figure out? What are these two sides going to be? Can somebody tell me what the length of the vertical side of this triangle is?
Yeah, we can use either the law of cosine or sine to find out the sine.
Okay, so which one do you want to use for this one?
We can use the cos. We can use the cosine.
Right, so what do we get? So if we use the cosine, what do we get for the length of the side?
Let us first name the two sides. Let's put some letters to the two sides.
Okay.
Because we just
so-
have two R over there.
Okay, so let's call this A and we'll call it B. And 500 is C. This is the third side.
So we know that the cosine is equal to, the cosine is adjacent over hypotenuse.
Right. So cosine of 55 degrees is equal to the adjacent
Over hypotenuse.
hypotenuse. And so what letters are those in this case?
The adjacent is the A and the hypotenuse is the,
The C. Right, exactly. Great. Okay, and so, and C is 500, right? So this is A over 500. Right. And so that means that we get that A is equal to,
So we have A is equal to the inverse of the cosine.
we don't need inverse, right?
Oh, no, yes, you're right. We don't need inverse because we already have 55 degrees.
Exactly.
Yeah. Okay.
So A is just what?
So A is equal to cos 55 degree, 500.
Exactly. So it's 500 times cosine of 55 degrees.
Yes.
And then we can do something similar with the B, right? With the sine. So thank you, Ed. Yeah, do you want to do the other side also?
Yes. Which is opposite or hypotenuse.
Right. So sine 55 is opposite over the hypotenuse, which in this case is B over C.
Yes.
And that's B over 500. And so we get that B is equal to
500 sine 55.
Exactly. Great. So A is 500 cosine 55 and B is 500 sine of 55 degrees. And so that's going to now tell us what this X and Y is, right? Because we're going to get that X is equal to, well, we're already at 250, and then it's going to increase by B, right? That's how far we're moving in the horizontal direction. So this 250 plus B is what X is going to be. So it's 250 plus B, which is equal to 250 plus 500 sine of 55 degrees. And then similarly, Y starts at 500, but then we're going to add A because we're going up by A. So Y is going to be 500 plus A, which is 500 plus 500 sine 55 degrees. Okay, and sine of 55 is not an angle that you generally know, so let me just...
Yeah, Andrew, it
Yes.
is cosine.
Oh, sorry, cosine, thank you. Thank you, sorry, that's a mistake. 500 cosine of 55 degrees. And so what we end up getting is that X is equal to, so what Y turns out to be 500 plus 500 cosine 55 degrees turns out to be 786.8 roughly. And then 500, so then we have 250 plus 500 sine 55 degrees turns out to be at 659.6. Okay, so we get that XY is equal to 659.6, 786.8. Okay, I'll box it in red. Okay, so this is how we solve this problem. And in this case, most of what we had to do is just draw the picture. There was just one thing that we had to figure out involving the bearing, and it always just means we just have to draw this right triangle and figure out what the two sides of the right triangle are. Okay, so are there any questions on this problem? Okay, good. So let's do the second homework problem. So this one we have John spots a crocodile directly north from his location. Sarah is 500 feet east of John and spots the crocodile at a bearing of 330. Okay, how far is John from the crocodile? Okay, let me just do everybody again. Okay. Okay. So how far is John from the crocodile? So again, like every bearing problem, we just draw a picture, right? So let's start with John. So here's John, right? And the crocodile, so here's John, and we can draw a little picture if we want, right? So here's John, and the crocodile is directly north from his location. So here we have, the crocodile. This, if we want to, we can try to draw it. I'm not very good at drawing. Let's try this. That's my attempt to draw a crocodile. Okay, so there we have John, and there we have the crocodile, and then Sarah is 500 feet east of John. So here's Sarah. Okay, so there's Sarah, and she's 500 feet east of John. So we have 500 over here. And then the question is, how far is John from the crocodile? Well, what do we know? We have one other piece of information, right? So the other piece of information is that the bearing that Sarah sees the crocodile at, that bearing is 330 degrees. So if we draw a line going directly north from Sarah, then if I try to draw the entire, and then I draw the line from Sarah to the crocodile, so let me draw that over here, then this entire bearing over here, then this bearing right here, all the way around, this is 330 degrees. So my question is, right, so we have John, we have Sarah, we have this crocodile, and we have 330 degrees. Okay, and what we want to figure out is how far is John from the crocodile, right? So John has his north line, and we can call this X, right? And what we really want to do is solve for X, right, when we have this. Okay.
Yes, I think.
Yes.
Hello?
Yes. Ed?
Yes. I think we start out by finding the little angle to the 330 degrees. Let's
Sure.
find a portion of the angle over there, then we'll be able to find the other one.
Exactly. Good. So which angle? So yeah. So what is the angle?
The
Right.
angle right to where Sarah stands.
Okay. So right at this angle?
Yes, yes.
Okay. And so that angle is going to be exactly right. 360 degrees minus 330 degrees. And so that's 30 degrees. And so now let me use another color. Let's use purple. If that's 30 degrees, then what's this angle? This purple angle right here.
Yes.
Right. So what should this angle be? The purple one?
So if that is, the angle you just found is how much?
So this angle is 30 degrees. So how much is this angle going to be? This purple one here? Hello, James?
Yeah, we can use the interior angle formula. We say A plus B is equal to 180, and we're having the value for 30.
Right. Well, it's not going to be 180, right? Because this is a right angle.
So
right?
you say 90?
So it's going to be 90, right? So yeah, so exactly. So what we're going to have is 60 degrees.
30 minus, that would be 60.
Exactly, right? Because what we're going to have is, let me just do it in the right colors. So we have 90 degrees, which is the full right angle here, minus 30 degrees, which is this part over here, gives us what's left. So that's going to be equal to 60 degrees. Okay, so we got 60 over here. And thanks, Rufus, for the answer in the chat. Okay, good. So now we know what we need to know, right? So we have X, we have 500, and we have 60 degrees. So what trigonometry function should we use to set up the equation? Tangent, right?
Exactly. Yeah.
So tangent of 60 degrees is equal to right? It's the
Opposite or
opposite.
adjacent.
Exactly. Opposite over adjacent. And so this is equal to x over 500.
X over 500.
Right. So x is
So
equal
X is
to,
equal to 500, tangent 60.
exactly. And does anybody know what tangent of 60 degrees is? So tangent of 60 degrees is one of these that's good to memorize. So 30 degrees, 45 degrees, 60 degrees, these are all facts that are good to memorize. So tangent of 60 degrees is the square root of 3. Okay, and it's a value that shows up a lot. So it's a good one to memorize. So this turns out to be 500 times square root of 3. And since that's an exact answer, we can just leave it what it is. Right, so x in this case is going to be 500 times square root of 3. So that's how far John is from the crocodile.
Hello.
Hello, yes. Tomas?
Yeah. So what's the value of 500 square root of 3?
Oh, okay. We can do that out with a decimal if you want. You probably need a calculator for that. So let me see. 500 square root of 3 is going to be about 866. It's about 866. Yes.
Hello.
Hello. Yes.
Hello.
Yes. Tomas.
I use another way to find the 666.
The 866.
Yeah, I use another way to find it.
Okay. How did you find it?
The 30 degree. Yeah, the 30 degree.
Mm-hmm.
The two long are parallel. So we have alternate angles.
Right.
So the 30 degree can be found on crocodile.
Yep. So did you draw? So did you draw this line here?
Okay, so the angle described by the position of the crocodile will be 30
Oh,
degrees.
I see. So you did 30 degrees here because of the alternate interior angles. This angle and this angle.
Okay, so I use tangent 30 degree and get the same value.
Right. Exactly. So if you draw this angle with the 30 degrees, then you can also use that tangent. So I'll just say we can do it over here. So, or you could use that tangent of 30 degrees is equal to 500 over x.
500 over X, that's the same.
Right. That'll end up being the same. So this is going to give you that x tangent of 30 degrees equals 500. And so x equals 500 divided by tangent of 30 degrees. And this, in fact, will also be equal to 866. I mean, it's the same answer, roughly 866. Yeah, so both methods work. Usually with right triangles, you can draw different triangles and still get the same answer.
Hello.
Hello, yes, James?
Yeah, so the constant for tangent 60 is the root of 3.
Yep.
So that's looking at the trigonometric table, you can find the root of 3 to be the constant of tangent 60.
Root of 3 is just, yeah, tangent of 60 is root of 3.
But using tangent 30, the inverse of tangent 30 gives you, using the same formula, the same value, you're getting the same value when you use tangent 60. So you are telling me that tangent 60 is equal to tangent 30?
Is equal to the inverse
that's
of
not the same
tangent 30,
value.
yes. So tangent of 60 degrees is equal to 1 divided by tangent of 30 degrees.
No, Dr. Obtus, now what he's saying, he said the same formula, but just look at the equation over there. You see 500 over X and X over 500. There are two different things over there. So just look at the two equations. Tangent 60 is equal to X over 500 and tangent 30 is equal to 500 over X. So look at the two equations. They are not the same.
Exactly, right. So what we have here is on one side, we have 500 tangent of 60, and then the other thing, we have 500 divided by tangent of 30, right? But these two things are the same. And the reason is because tangent of 60 is the same thing as 1 divided by tangent of 30.
That's what I'm saying. Tangent of 60 is equal to the inverse of tangent of 30.
Right, exactly, yeah.
Yeah, that's what I want to get clear.
Yeah, it's the inverse of tangent of 30, exactly. Okay. Other questions about this problem? Okay, so let's do one more bearings problem that was in the notes. So some people already did this, but I want to do it in person today. So this one is a little bit more complicated, and sometimes I've seen questions like these on some of the exams. So now we have three ships A, B, and C, and the bearing of C from A is 135. The bearing of A from B is 45. And then we give some distances too, right? So if A is 8 kilometers from B and A is 6 kilometers from C, then we need to know how far is B from C. So again, it's complicated when you look at it, so you've got to draw the picture to know what's going on. So I'm going to start with A. This is A. Then the bearing of A from B is 45. So that means to get from B to A, you have to go up and to the right, right? That's what a 45-degree bearing is. So when you draw your picture, you have to draw everything in the right place. So here, I have to draw B like this, right? Because I want the bearing of B from A to be 45 degrees, right? This should be 45 degrees. And now, what else do we have? We have that the bearing of C from A is 135. So this we can just follow around, right? We're going to go from A to C. So I'm going to do around 135 degrees. So it's going to point in this direction. Okay, so let me draw in this direction, and we're going to go not as long. So maybe like this. This is going to be C. Okay, and we know that the length from A to B is 8 kilometers. And the length from A to C is 6 kilometers. Okay. And so now we draw a line from B to C, right? And we want to know how long this line is, right? We want to call this X. And the other thing, the one thing I forgot to label here in the diagram is we didn't yet use that the bearing of C from A is 135. So I have to label this angle here. This angle is going to be 135 degrees. Okay. And so now the question is, all right, we have a triangle. It has two sides. One is 8 and one is 6. But knowing two sides of a triangle is not good enough to figure out the third side, right? If you want to figure out the third side, then you also need to know the angle between these two sides, the angle between the AB and the AC. So the key to solving this problem is we need to figure out what this angle here is. Okay, so I know some people know how to do it because some people handed in correct solutions to this problem in the email or in the chat. So if we wanted to figure out angle A, what's the measure of this angle A? How could we do that?
Please come on again.
So I want to know what is angle A. So I'm going to draw this angle in red. And I want to know what is the measure of that angle. So does anybody have an idea just from this information? I claim all the information you need to know is here in the diagram already. So just from this information, how would we figure out this angle?
Hello?
Hello, yes.
Yeah, I found 90 degree.
Yeah, that is correct. How did you find that?
It's very hard to explain, but this line coming from A.
Mm-hmm.
Okay, it goes straight down. So yes.
Mm-hmm.
Another one going vertically.
Right. Should I draw? Do you want me to draw this down like this?
Okay.
I mean, if you
Yeah.
do you want that line or not?
Yeah, another one horizontally.
Oh, horizontally. Okay. Okay.
Yes.
Like this.
Okay, good.
Yeah.
So okay, the 45 degree in B, the 45 degree in B will be alternate angle.
Right.
So so the first side will be 45 already.
Right. Oh, okay. I see what you're saying. So this angle here for the alternating angles, this is 45.
Okay, 45.
Yeah.
And it didn't draw in C. In C, can you do the same thing in C?
Okay. So you want me to draw a vertical line from C?
Okay. Hello?
Hello, yes. You want me to do this?
Okay. Up, we have 135 degree already, right?
Right. And so over
135,
here, oh, you want me to do the same thing over here? I see. Okay. So you want me to draw this angle now, right?
Okay, so you get 180 from there to there, that 180. So 180 minus 135, you get 45 there.
Exactly, right? Because here we have that 180. This is a straight line right here, right? So we have 135. And so what we need over here is 180 minus 135, and that's going to be 45 degrees. So 180 minus 135 is equal to 45. And so both of these are 45 exactly. And so 45 plus 45 equals 90. All right, very good. That's perfect, right? So we have that these two angles together add to 90 degrees. Another way of doing this, by the way, is you know that if the bearing of B from A, sorry, the bearing of A from B is 45 degrees, then you know that the bearing of B from A, you have to add 180. So you know that that will be 225 degrees. So you know that the entire angle over here from A over to the line to B is 225 degrees. And if you know that this is 135 already, then you would know that, you know, the angle at A would be equal to 225 minus 135, and that would be 90. Okay, so this is another way of doing it. Okay, but in any case, so this is a 90-degree angle. Okay, thank you, Tomas. Okay, so if I have a 90-degree angle and I have a triangle with a side of length 6 and a side of length 8, and the angle between them is a right angle, then how do I figure out the length of X over here?
Please come on again.
So I want to figure out X, right? So we figured out this angle. It's 90 degrees.
So you use Pythagoras theorem.
Exactly. Thank you, Clinton. Right. So we've got 6 squared plus 8 squared is equal to X squared. This is Pythagorean theorem. Right. And so that's 36 plus 64 equals X squared, which is 100 equals X squared. And so 10 equals X. And so the answer is 10 kilometers. Okay. All right, so the answer here is 10 kilometers. That's how far B is from C.
Oh yeah.
Yeah.
I think I look at these. I look at the figure over there, but all people solve correct. But I think I have different version. If you look at similar triangles,
Okay.
If we split it into two triangles, like you already said, that is 45 is alternate, so that is 45. Then we compare this triangle A to triangle B. Say since this is 45, that also be 45. That will give it 90.
Yeah. So that'll work also, right? Yeah. So we have some similar triangles, right? So I think this triangle here is similar to this triangle over here, and which is similar to this triangle over here. They're all right triangles with 45 degrees.
Okay.
Now, yeah. So all of that will also work, right? When you have an alternate interior angle and then you draw parallel lines, then you're going to always get similar triangles. In fact, you'll get congruent triangles over here. And so here's a question. Maybe this is not part of the question. The answer is 10. But let's say that the angle turned out to not be 90 degrees, right? We got lucky. This angle was 90 degrees and we could use the Pythagorean theorem. But let's say, maybe I'll do this on another page. Suppose we had a triangle, kind of similar looking triangle. This is A, this is B, this is C. Let's say that we had 8, 6, and then this was just some angle theta, where theta is maybe not equal to 90 degrees. And then we had X. So how would we find X? Because this could show up in a bearing problem also. Let's say we know the triangle, that we know all the angles, so we got this. So the question is, how would we find X in this case? If I know the 8 and I know the 6 and I know the angle, but the angle is not a right angle.
Yeah,
Yep, Clinton?
we could find X by using the cosine law.
Exactly, right? So use cosine law. So Clinton, do you want to just set up the equation there?
Yeah, sure. So the equation will be X squared equals 8 squared plus 6 squared minus 2 times 8 times 6 cosine of theta.
Exactly. That's great. So that's exactly right. And so if we then wanted to simplify this a little bit, this would be X squared equals 100 minus 2 times 8 times 6 is 96 cosine of theta. And so this gives us that 96 cosine of theta is equal to 100 minus X squared. Well, oh, no, never mind. There's no reason to do that. Okay, so this is it. And then you just have to use a calculator. You just have to solve this, use a calculator. Okay, so we got lucky that we had a right angle, which means that it was easy to do by hand. But in general, even if it's not a right angle, you can always use the cosine law to figure out what the third side is going to be when you have two sides and you have an angle between them. And so if you have any bearing problem with 3 ships or 3 airplanes or 3 people, sometimes you might get a triangle where you know what 2 of the side lengths are and you know an angle, but it might not be a right angle. So to finish the problem, you'll have to use the cosine law to make that work. Okay, any questions on this?
Yeah,
Yes. James, yes.
S squared is equal to 8 squared plus 6 squared. That is, S is representing the C value right in the Pythagorean theorem, right?
Exactly, yes. You mean on the previous page here?
Yeah, you can't S was in that position. That's why the next page, the page you're solving on.
Right. So in this is the cosine law. The general thing you would have is the general cosine law is you would have C squared equals A squared plus B squared minus 2AB cosine theta. And in our case, X is representing the C, 8 is representing the A, and 6 is representing the B. And so that's how we get this equation here with the X squared equals 8 squared plus 6 squared minus 2 times 8 times 6 times cosine theta.
Yeah, so I'm saying that in case in the problem where you have the value for X, but the point, the position 8 is in, you don't have the value for that position. Will you still use that cosine law?
So sorry, so you have the value of X. So if you're given X, you know X. But what don't you know? But you don't know what the angle is?
You know the angle, but the position 8 is in a position that you don't know the value.
Okay. So for instance, let's say that we had, if instead of the 8 and the X, if instead we had like the X over here and the 8 over here. Is that what you're asking? Yeah. So yeah, you can still use the cosine law. Yeah, that's fine. You can still use the cosine law. And so, okay, well, the problem is for this one, it's probably, okay, so no, yeah, let me change that. If you only know 2 sides of a triangle and another angle in the triangle, but it's not the angle between the 2 sides, then you can't always solve for X. So sometimes there could be 2 different possible values for X. So what happens is if you have, maybe I'll write this on a new page. So let's say that let's say that I have a triangle like this. Let's say that I have 8, 10, and X. I want to solve for X, and I know this angle theta. The problem is that if I use the cosine law, what happens? I get 10 squared equals X squared plus 8 squared minus 2 times 8, or I'll say 2 times x times 8 times cosine of theta, right? Or to simplify this, this is 100 equals x squared plus 64 minus 18x cosine theta. And then I'll subtract 64 from both sides. And this is going to give me 36 equals x squared minus 18, sorry, not 18, 16x cosine theta. And this is going to be x squared minus 16x cosine theta. And, or in other words, I could write this as x squared minus 16x cosine theta minus 36 equals 0. And now what's the problem here? What kind of equation is this? This is a quadratic equation.
That's quadratic equation.
Exactly, right? So this is a quadratic equation, and a quadratic equation can have 2 solutions. Okay, and so a quadratic equation can have 2 solutions. And what that means is that you don't necessarily know the exact value of x, right? You can only narrow it down to 2 choices here. Okay, so you can't, so I'll just write this up here. So that means with a quadratic equation with 2 solutions, you can't solve for x necessarily. Now, it might happen that one of the solutions is positive and the other solution is negative, right? If one is positive and one is negative, then you know what x is, because you have to take the positive solution, right? The negative answer can't be x. So if you get that one solution is negative and one solution is positive, then you're okay. You can solve the quadratic equation for x and it works. But if you get 2 positive answers, then x could be either one. Then there's not enough information given to solve for x in this case. Okay, so depending on what the angle theta is, you might get 2 positive solutions, or you might get a positive and a negative solution. Okay, and so that's the problem. So when you have the angle is not the angle in between the 2 sides, then you're sometimes in trouble. You might not be able to solve. But when the angle is the angle between the 2 sides, then you can always solve. Then it's always okay. Yes, this is a great question. Yeah, Clinton?
Just a quick comment. Can we say that the cosine law can only be used on triangles where we have 3 sides, like side, or sides, angle, side?
Well, I mean, again, we saw this. In this case, we have side angle, right? And so the cosine law can still sometimes be used, right? I mean, if we have side angle, right? It's not side angle side. And if we're lucky and this quadratic equation only has 1 positive solution, then we're okay. Then we know that it will work. But exactly, but it might not work. Whereas if you have side angle side or side, then the cosine law will always work to solve the triangle.
Okay.
Yeah. Side angle, it might work or it might not work.
Yeah, bro, Andrew.
Yes. Yes, Prince.
Yeah, since it's looking this way, where the angle is pointing up, then we have 2 sides given in this triangle. But
right.
You know, we cannot use the Pythagorean theorem to find the x value, and then in our process, then we use a law of cosine what we use from the previous stage, then we find the angle right here. Can it be?
Right. So the problem is we don't have enough information. So I'm assuming in this case, I'm assuming that we're given the angle, that we know the angle already. If all that I know is 2 sides and nothing else, then I can't find the angles. So usually, because it's a bearing problem, you usually have enough information to find the angle that you need, right? So if I just give you a triangle and I say it has sides 8, 10, and theta, what's x? Then you can't solve for x because you need to know theta in order to find x. But usually, if this is a bearing problem, then maybe we would know something. Maybe we would know that theta equals like 30 degrees or something like that. And if I know it's 30 degrees, then maybe I can't solve for x. But at the very least, I can narrow x down to at most 2 possible values. And if they're both positive, then I don't know which one is which. But if one is positive and one is negative, then maybe I can solve for x.
Yes. What we can do if it is two positive answer, we prove it. We take the first value, we substitute it to be x, and then we solve again.
Right,
Yeah,
but both of them work. Right? So let me yeah, so let me try to draw another picture.
For this one, we'll have one positive answer and one negative answer. Because of the factoring pattern here. It'll be one positive answer and one negative answer.
Okay, right. In this case, that'll be right. But if I just draw you a triangle, I can make an example where you might get two different positive answers. Right, I can make an example with two different positive answers. So for instance, if the theta is very narrow, I think, how do I want to draw this, right? I think if theta is very small, then it's possible to have two different positive answers. Oh no, in this one, it's going to be okay. No, you're right. You can't have a positive and a negative answer in this case because you have that this 36 is negative. That's right. So in this case, you can't have that. I'm getting confused now. So in general, right, if you have two sides and an angle, that is not good enough to solve for the triangle. So I'm just trying to figure out when this causes problems. Let me think about this a little bit more, and I'll give a nice presentation of this next week. I don't want to do this. I don't want to try to do it on the fly. Let me prepare this, and I'll be able to talk about it well next week.
Okay.
Yeah. Right. Because as long as this thing is negative, then you should always have a positive answer and a negative answer. Right. You shouldn't have two positive answers. Okay, but there are times that you can have two positive answers. So, right. So, x squared. Right. So 8 squared equals x squared plus 10 squared. Yeah. So for instance, if instead I have the theta, if instead of having theta over here, if instead I put the theta over here, then I can have a positive answer and a negative answer. Because in that case, then the 10 and the 8 are going to be switched. Let me talk about this more next week. So next week I'll do an example with two possible answers. Okay. So I'll prepare a good example for that next week. Okay. Okay. All right, great. So let's just move on. So we have about 10 minutes left. So I just want to talk about the beginnings of this new unit. I just want to introduce what these objects are that we're going to be talking about. So this semester is really about linear algebra. So it's about matrices and vectors and a little bit about the interactions with trigonometry. So the people, again, who were here in the spring, then you saw matrices, but not everybody was here in the spring. So I just want to recall very quickly what a matrix is. So a matrix is a rectangular array of real numbers. So you can just write it, in a box. So you could have a matrix like 1, 2, 4, 3. It doesn't need to be square. So you could do 1, 2, 3, 4, 5, 6. You could have 2 rows and 3 columns. You could have 3 rows and 2 columns, and you can have negative answers. So -1, 3, pi, 27, 1000, and negative 2.4, right? I mean, this is a perfectly fine matrix, right? Any way that you put a bunch of numbers in a rectangle is called a matrix, okay? And if m is the number of rows of the matrix and n is the number of columns, then we call the matrix an m by n matrix. And this is called the size of the matrix. So in this case, the matrix here, this is a 2 by 2 matrix because it has 2 rows and 2 columns. This is a 2 by 3 matrix because it has 2 rows and 3 columns. And this over here is a 3 by 2 matrix because it has 3 rows and 2 columns. Okay. And sometimes if you have only one row, we've already seen row vectors and column vectors, right? So if we have only one row, so a matrix like 1, 2, 3, 4, this is a 1x4 matrix, or sometimes it's called a row vector because it looks like a vector and it's just in a row. And likewise, if we have only one column, so let's do the same thing, but in a column, 1, 2, 3, 4. This here is a 4x1 matrix. It's got 4 rows and only one column, and this is called a column vector. Okay. Any questions? Okay.
Yes.
Yes.
Yes, sir.
Yeah, Rufus or Prince. Yeah.
The symbol what we have here are this bracket. Can different symbol be used to represent in a matrix with a exception on the bracket?
Yeah, I mean, you can use different symbols. So, I mean, I could write something like, I don't know if this is your question, but I could write 1, 2, 3, 4, or I could write, 3/3, 2, 3, 4, right? This is the same matrix. But, but symbols, I mean, usually we use a capital letter for a matrix. So I'll call this a matrix A, but I could also use like V because because it's a vector. So I'm not sure if I'm answering your question, but usually we use a capital letter for a matrix. But if the matrix is also a vector, you could also use a vector notation for it. Is that okay?
What I was saying is, as well as different symbol, like a different symbol like this can be used instead of the bracket that is used.
Oh, instead of the brackets. Yeah, sorry.
Can you use other thing?
Yeah. So I like to use brackets, but sometimes you'll see big parentheses. So you'll see something like 1, 3, pi, 27, 1000, and minus 2.4. So sometimes you'll see parentheses also. But parentheses or brackets, they mean the same thing. You can use either one. Okay. Yeah. So either one. Sometimes with vectors, you're more likely to see parentheses instead of brackets, but both of them are fine, and you can use them whenever you want. Okay, so the last thing I want to do is just recall that if I have two matrices, I can add them and I can subtract them. And I just do it element by element, right? So it's just the same thing that I do with vectors, right? So if I have 1, 2, 3, 4, and I want to add 5, 6, 7, 8, then what do? I just add the elements, the entries in each position. So here I just do the 1 plus the 5. 6, exactly right. So here I do 2 plus 6. Here's 3 plus 7, and here's 4 plus 8. So if I want to write that out, that's 6, 8, 10, 12. Okay, so I can add matrices as long as they're of the same size. That's the key. They have to be of the same size. So similarly, if I have 1, 2, 3, 4, 5, 6, and I want to subtract a matrix, so let's say I'm subtracting the matrix 0, 1, 2, 3, 4, 5, then I'm going to get 1 minus 0, 2 minus 1, 3 minus 2, exactly, 4 minus 3, 5 minus 4, and 6 minus 5. And this is otherwise known as just 1, 1, 1, 1, 1, 1. Right? So I can add and subtract matrices the same way we do it with vectors. Vectors, the numbers are in a line. With a matrix, the numbers are in a rectangle. But adding and subtracting is exactly the same. You just take two matrices and you can add them, or you take two and you subtract them. You just do the addition and the subtraction on each entry, one at a time. Yep.
Yeah. Can you have a new value in matrix like X?
Yeah, I mean, so you want to call a variable, you want to use a variable for a matrix?
Yeah.
Yeah, that's fine. But usually we use a capital letter instead of a lowercase letter. So you might use A or B. These usually represent matrices.
Hello.
Hello, yeah, Rufus?
Yeah, it is possible to add or subtract two matrices if the dimensions are not the same.
No, it's undefined if the dimensions are not the same. So the matrices absolutely have to be of the same size. So size means dimensions. So they have to be of the same size if you want to add or subtract them.
Okay.
Okay. So the last thing I want to do today, this is just easy because I want to do this so that you can do the homework. The multiplication will wait until next time. But so if I have a matrix and I have a real number, then I can multiply the matrix by a real number. Just like with a vector. If I have a vector, I can multiply it by 2 or by 3. I can do the same thing with a matrix. So if I take 3 times the matrix, 1, 1/2, 0, and I don't know, 1.4, I can multiply it with a scalar. And all that I do is it just means that I multiply each entry by the 3.
3 times 1, yes. Yes.
Exactly.
Yes. That's correct.
So in this case, I'm just going to get, 3,
3,
3/2, 0,
0.
4.2. Right. So I can take two matrices and add them and subtract them. And I can also take a matrix and I can multiply it by a number. Okay, and I just do it by multiplying every entry in the matrix by that number. Okay. And so the last thing that I want to do, and so we'll finish in a couple of minutes, is you can solve equations with matrices. So this maybe gets to your question, James. You can solve equations with matrices just like you can with the real numbers. So maybe I'll do this on another page just so that we don't run out of space. But so if I have the equation 2a plus 1043 equals 4726, right? I can solve for this exactly the way I would a standard equation. I just subtract 1043 from each side. And I subtract 1043 from each side, and I get 2a equals, well, now I have 4726 minus 1043. So that would be 3, 7, minus 2, 3, right? Because I'm subtracting. It's 4 minus 1, 7 minus 0, 2 minus 4, and 6 minus 3. And then I can just divide by 2, right? I can just do the same thing, dividing by a number as I do with a regular number. So a then just turns out to be 3 over 2, 7 over 2, minus 1, and 3 over 2. Okay, so this is the answer. So you can solve like a standard linear algebraic equation with matrices the same way you would do it for numbers, right? There's no difference. Okay, so maybe that's all I'm going to say about matrices today because we're out of time. But next time we're going to multiply matrices, which is a little bit harder, but turns out to be very useful. And one of the things I want to try to get across in this course is, what it means to multiply matrices, because matrix multiplication is going to have this very strange formula when you write it down. It seems like a very complicated formula. It's not just you take the entries and multiply them together. It's a complicated formula. And so in math, you don't just invent a complicated formula so that you can have a complicated formula. You invent a complicated formula because it does something, because it tells you something. And it turns out that this matrix multiplication has a real geometric meaning. It really corresponds to doing things like reflections and rotations and dilations, and all of these geometric patterns can be encoded with matrices, and multiplication turns out to correspond to doing more than one pattern operation. So that's going to take a little bit of time to see. We're not going to do this matrix multiplication today, so we'll do that next time. But yeah, so in the meantime, there's going to be some homework, so I'll send out the notes. But the first thing is, in the bearing problem that we did, we calculated this triangle, but now I want to know, what we didn't do was calculate the bearing of B from C, right? So if I go back to this diagram, where's the diagram? Here it is. Here it is, right? So we calculated in this case that x is equal to 10. but we didn't actually calculate the bearing of B from C. So in this picture, it looks like they're on a horizontal line, but they're actually not. Okay, so this is the first homework question, is to try to figure out what's the bearing of B from C here. And then the next two questions are just matrix questions. The first one should be pretty straightforward, and then the second one maybe requires a little bit of thinking. So the first question is just, if A is this matrix and B is this other matrix, calculate these expressions, A minus 2B and 3A minus B. This should be pretty straightforward. And then the third question is, for these same matrices, A and B, is it possible to find constants C and D, which give you CA plus DB equals 2751? Okay, so this one is straightforward. And this one is not, it's not that hard. It's not a very long solution, but this requires some thought. Okay, and maybe I won't give any more hints on this. And so next time, we're going to further discuss matrices. So in particular, we're going to talk about matrix product, matrix inverse, and matrix transpose. And maybe, if time, there may not be time, but if time, also determinant of a matrix. Okay, and so most of the rest of the class is going to be about matrices, and we're going to relate matrices with vectors, and we're going to relate it with all kinds of geometry. Okay, so I think that's it for today. Thank you for your attention. As always, I'll send the notes, and I will send the recording. This week, the recording is going to be on YouTube. So what I'll do is I'm just going to send you a link to the recording, and it's just going to be a link to a YouTube page where you can watch the recording. Okay. Sange, anything you need to say?
Thank you for the day. I don't have anything to say.
Okay.
Thanks everybody for coming. Let's try to